Today we're going to be talking about gravitational fields and the forces that lie within different gravitational fields. Going through this topic, what I want to cover is some of the historical background where the ideas of gravity have come from previously and to where they sit today. Also want to talk about what are fields. It's important that as students studying VCE Physics that you're aware of what fields are. This applies not only to gravity, but also when we talk about electrical fields. We can't talk about gravitational fields with going over Newton's universal law of gravity. This is very applicable to a lot of calculations that you're doing in VCE Physics, but a lot of calculations that are carried out with space exploration, satellite motion, various forms. And I want to also have a look at the inverse square law because I think it's a component that you really need to understand as to why certain formulas are derived in the way that they are, but also what happens with the intensity of energies as they get spread out over a vast surface area. Okay, so let's talk about the historical background. Well, when we think of gravity, most people will think of just Sir Isaac Newton. However, the story of gravity really relies on two colossus of physics. Sir Isaac Newton, obviously, who's commonly deemed as the father of modern physics, and Einstein, Albert Einstein, who really came up with special relativity, general theory of relativity. We have gone over the theory of special relativity, which speaks about, if you like, time dilation, length contraction, and really light being a universal speed limit, if you like. But Einstein's general theory of relativity really applies to when we're talking about gravity, because general relativity actually introduces to the fore this concept of space-time. All right, so when we're thinking about Newton, a couple of things to understand about Newton and his ideas. Okay, the first idea, you may have heard the story of an apple falling on Newton's head, and Newton then coming up with the theory of universal law of gravity, that bodies will want to naturally be attracted to one another, or they will be attracted to one another. But Newton really identified gravity as, if you like, a universal pull. And sometimes we can swap this term pull for the idea of a universal force, which is not bad, but the idea is that bodies naturally are pulled together by gravity. Okay. Now, there's nothing strange with these ideas. They're actually very beautiful. But one of the very important things about Newton's ideas on gravity is they're very accurate. The equations that Newton came out with in the late 1700s were actually very accurate. However, Newton had a big problem. He didn't know what gravity was. He couldn't explain what gravity was. And then it was all the way up until the early 19th century or 20th century that Einstein came along. And Einstein had this idea of space, what we call space and time. And the way that he revolutionized this idea of gravity is he combined space and time into this one kind of component called space-time. And what it was is it's like space and time being woven together like a fabric. And what would happen with gravity is the warping. I like the term warping, but more technically what we call is the curvature of space-time made by a body. So I'm just going to say that Einstein put forward, especially in his general theory of relativity, is that gravity is the warping of space-time made by a body. So here we have an image of an example of what. Sorry. Here we have an example of what Einstein is sort of thinking about. So, and the example that I'm sort of highlighting is just this image here. So what Einstein is thinking about is, here we might have a plane of existence, okay, with sort of a grid formation, and we call this space-time. And what would happen is we would take this plane of existence or plane of space-time like so, and what we might do is we might put a large body in the middle of it. And that large body would, sort of like a ball resting on a trampoline, would force little bits of curvature to come around. And these curvatures would be seen like so. Okay? And we might have curvatures looking like that. And we get an indentation. Apologies for the drawing, I know it's not great. But we get this idea of a body actually warping space-time and creating, if you like, a warp or a bit of a indentation in the field, in the gravitational field. And what happens then, if we put another smaller object to it, this smaller object will naturally be attracted to the larger object. And vice versa, the larger object is also attracted to the smaller object, because this smaller object also creates its own indentation of the fabric of space and time. So that's a general idea of the curvature of space and time, which is really important when we think about gravity. So the way that we approach gravity, though, is we look at it as fields. And a couple of ideas which we need to appreciate about fields. Fields, first and foremost, are vectors, or what we call vector fields. And here we have an example to the left. And for any one vector, we can take this vector for example. Okay, each vector has a direction and a magnitude. So it's virtually a quantity with a direction. And what we can see with the example of these fields is that the gravity field always points towards the body. So you can see here that each of these fields, regardless of where they are, the field is pointing into the body, which is making that indentation in space and time. And what we got to understand is, as we approach the body, gravity increases. Okay? So what we're saying is, within that, gravity increases as we get closer to the body. Okay. What we would also say, we could also term it as, the field strength is getting greater as we get closer to the body. But that's really how we have to understand fields. The next thing that we need to talk about is Newton's universal law of gravity. Now, Newton had a formula which is still used today. It's still very applicable today. Okay, and his formula is written as r squared. Now, a couple of features of Newton's. This is the gravitational constant. So the gravitational constant is a value that you are all going to have to remember, and it's 6.67 times 10 to the negative 11, okay, Newton meters squared kilograms. That's what the gravitational constant is. And when we talk about the gravitational constant, what we're talking about is two bodies, and we don't look at their volume per se, we look at their mass, how much matter they have, because matter is what actually causes the curvature of space and time, not volume. So just make sure you make that distinction that matter or mass is what makes the forms the curvature. So what we have is we have two masses. Okay, I would just fix this up. Mass 1, mass 2. Okay, obviously they're set apart by a radius, which we have here, r squared. And what we have is these two masses will be attracted to one another via a force. And the way that we calculate that force is by using Newton's universal law of gravity equation. Now, the other thing that we can do with Newton's universal law of gravitation, if we apply that force is given by mg, okay, mass times gravity or acceleration, and that's the gravity that would be at any point away from a given body. We can say that the mass 1 being, if you like, Earth, and this mass here, so this mass here might be me, okay, and I'm set at a certain radius from the Earth, okay. This mass here is Earth, okay, and like I'm saying, I've set myself a distance away from Earth. What we can do is we can cancel out the masses, and we can find what gravity I would be experiencing if I was set away from a larger body. So for example, this might be our Earth here. Okay, that's Earth. Here I am in outer space. Okay, I'm obviously set at a distance r. Now, another thing for us to consider here, and I've just made a little bit of a mistake here, is that the radius is taken from the center of the body, not the outer end of the body, the center of the body. So when we are dealing with the Earth, we have to actually make sure that we're talking from the center of the body. So I can find what gravity I would be experiencing if I was set maybe, halfway between the Earth and the Moon. Now, obviously, my gravity is going to be a lot less because I'm not close to the larger body. Therefore, the strength of the field acting on me is a lot less. All right? But these two equations are really two equations that you have to be familiar with. Okay. Now, the other interesting thing is this idea about the inverse square law. Now, I'm just going to here write F equals Newton's universal law of gravity equation. So here we have the equation, and really what I want to focus on is why have we got G and why have we got R squared? Well, if we look at this diagram, we can see that this R squared is really about how much force is being exerted over a set area. So, for example, with this area, initially, what we can say is that this area, or the force is spread out over a certain amount of area. If we take it out of space, same force, so the force is still there, but it's been spread out over a lot larger area. And likewise, if we take it further out, according to a sphere. And what it means, it's sort of like the concept is a little bit like density, you know, how much force is operating over a certain area. And this is why we have an inverse square law. Now, sometimes people write Newton's law like so, and that's when we know the two masses, but it's proportional to 1 on r squared. And what it means is the field strength, you know, gets less and less because it's less dense, if you like that for a term, as we get further away from the center of the body. And that's really important to understand. And when I'll just say here, when you're making your calculations, always make sure that you're squaring your radius value. Okay? You must square your value.